Hi class, Mr. Morris. We are talking today about enthalpy. We're going to go through several different concepts in this video. We've brought up enthalpy once before. It is the heat content of a system. Delta H stands for the change in enthalpy of a system. Remember, delta always means change. The enthalpy of a reaction, represented by delta H Rxn, is what we use when we're talking about the enthalpy of a chemical reaction. So in the last set of notes, we did talk about enthalpy, but it was always in terms of phase change. So we talked about enthalpy of solidification, if we're freezing something, or fusion if we were melting something, vaporization if we're boiling something. Now we're talking about actual chemical changes, and there's two different values. You've got enthalpy of reaction and enthalpy of combustion. Those are the two we're going to be talking about today. Enthalpy of reaction is the heat that's absorbed or released, so it's heat absorbed or released by a reaction or process for 1 mole of the reaction. This is a really significant difference here. Okay, the enthalpy of combustion is the heat absorbed or released by burning 1 mole of the compound. Okay, here's our significant difference. This is moles of reaction, this is moles of compound. They're not always the same thing. Often they're not. All right, our units are going to be pretty similar. It's going to be kilojoules per mole usually. It might be in joules per mole, but usually we want that in kilojoules per mole. The first one, enthalpy of reaction, is going to be in terms of moles of reaction, of course. And then our enthalpy of combustion is in terms of moles of the compound. So you're going to end up doing just the heat or the enthalpy that's produced divided by the number of moles that were consumed in the case of combustion, or the number of moles of reaction that occurred in the case of enthalpy of reaction. We're going to do some examples and it'll make more sense then. Okay, a lot of what we're doing today has to do with stoichiometry. We can actually think of heat as a reactant or a product. You can think of heat in terms of stoichiometry. So if we have a chemical equation, this is a generic chemical equation that's given, so we're assuming that this is a balanced equation, and we've got our coefficients A, B, C, and D. Well, down on the bottom when we're doing stoichiometry, we would always put the coefficients in terms of moles. That's going to be the bottom part of our fractions in a proportion when we're doing stoichiometry. You can think of the heat of the reaction, delta H of reaction, in kind of the same ways. Since it is in terms of moles of reaction, kilojoules per mole of reaction, we could just take the number of kilojoules given in the reaction and write it down here. That could be the bottom part of a proportion if we're looking for kilojoules, just to give a general idea. Okay. So we can calculate or use the delta H of reaction values using the proportion method that we use for stoichiometry. When you're given the information in the problems, when the given information in the problems, are not in moles, so the given information is not in moles, as usual, we're going to convert to moles before we do the stoichiometry technique. That's nothing new. It's the way we've always done stoichiometry. And when the asked information in the problem is not in moles, you convert from moles into whatever you're looking for after you've done a stoichiometry technique. We're going to use the next question as an example, but before we do, we want to identify some things. Oh, and by the way, just to clarify, this up here may look a little confusing. This top part, K, N, P, Q, Q, I'm just using letters to represent what's given or asked for in the question. That's all that is. Okay. And then down here, when we've got our coefficients, okay, that's the coefficients from the equation, from the balanced equation. Nothing new really, it's just written out in a little different way because this is a longer form of reaction. We've got a lot involved. Okay, we're going to use the next question as an example, but first let's talk about the information that you can glean from this equation. All right, the first thing that I notice is what 1 mole of reaction is. So we want to know some information about the combustion of ethane. 1 mole of reaction is based on the balanced equation that's written up here. In other words, if I wanted to describe it, I would say that 2 moles of ethane reacts with 7 moles of oxygen to produce 4 moles of carbon dioxide and 6 moles of water. This reaction, it either needs or produces heat. Well, this is negative. It's a negative value, so that tells me that it's got to be exothermic. That means it is producing heat. So one way you might see this written sometimes, and if you find it useful, you can try to do this. You could think of that as a product. We could say plus 3120 kilojoules. Okay, it's produced. Or you could say it's a product. Okay. So it produces, doesn't need it, it produces 3,120 kilojoules for each mole of reaction, for every 1 mole of reaction. Delta H of combustion, so this is a little bit different, for C2H6 is going to be a smaller number than that. The reason is because we have 2 moles of C2H6 for the balanced equation. Remember, this is the heat of the reaction. I want to know the heat of combustion. Heat of combustion of that is going to be for 1 mole of it. So if this amount of heat is produced when I burn 2 moles of ethane, the amount of heat produced when I burn 1 mole of ethane will be half as much. So I would just take negative 3,120 kilojoules per mole of reaction. Remember, that equals negative 3,120 kilojoules per 2 moles of ethane. That's what we're saying. It's divided by 2 moles of ethane. So if I wanted to know the delta H of combustion, it's going to be the number of kilojoules in 1 mole, which means I've got to divide by 2. Okay, that's essentially what I'm doing right here. I'm dividing by 2. And I get negative 1,560 kilojoules per mole of C2H6. Negative 1,560 kilojoules. And we should say kilojoules per mole of ethane. Remember, this is because the heat of combustion is for 1 mole of ethane, C2H6. That's why we did all of that. Okay, so the main difference between heat of combustion and heat of reaction, if we're talking about a combustion reaction, is heat of combustion is for 1 mole of that substance instead of just 1 mole of the reaction. Let's look at an example. Use the reaction above to solve the following problems using stoichiometry. We're going to calculate the energy that's released when 4.60 moles of ethane is combusted. Okay. This, by the way, is ethane. If you didn't know what it was, that's ethane. You can kind of deduce that because we know this is oxygen, carbon dioxide, and water. All that's left is ethane. Okay, so if I have 4.60 moles of ethane combusted, that's my given. I would put it up here, 4.60 moles. 2 moles is the coefficient. I want to know the amount of energy that's released. Okay, well, the energy is negative 3,120 kilojoules for every 1 mole. So that many kilojoules are being released. And I want to know X kilojoules, because this is written in terms of kilojoules. All right, so we're going to set up our equation. I have 4.60 moles of ethane, which is C2H6, over 2 moles, C2H6, equals X kilojoules over, and the number of kilojoules is negative 3,120. Kilojoules. Then we can cross multiply and solve for X. 2x equals 4.60 times negative 3,120. I know you can do that kind of math. Then you would end up dividing by 2 and you'd solve. We end up with x equals negative 7,180 kilojoules when we round to 3 significant figures. That's part 1, the energy released when we combust 4.60 moles of ethane. Okay, we want to calculate the energy released when 45.6 liters of carbon dioxide is produced at 1.00 atmospheres and 565 Kelvin. We want to know energy released. Switch pen color. Energy released. We've got liters of carbon dioxide. We've got atmospheres, and we've got Kelvin. Now that sounds familiar. That sounds to me like a gas law problem because I've got carbon dioxide, which I know is probably a gas, and I have volume, pressure, and temperature. I'm going to use our gas law, PV equals nRT. And of course, what I'm looking for in this case is the number of moles. So you could rearrange this so that we end up with N equals PV over RT. Just kind of a rearranging technique that you might find convenient for this particular problem. All right, so if I do that, I can just say N equals, think about pressure being, it's 1.00 atmospheres. Okay, volume, 45.6 liters. And then we have R, which is 0.0821. I think on the AP exam it's actually 0.08206, but you're going to get really close to the same answer, and you wouldn't be counted wrong for rounding here. Liter atmospheres per Kelvin mole. And then temperature is 565 Kelvin. By the way, if you look, our kelvins cancel out because of that. Our moles are what's going to end up being left on the other side. The liters cancel, atmospheres cancel, so it makes sense that we would end up with moles being our answer. N equals, after doing that math, 1 times 45.6, and then we divide by 0.0821 and 565. You're going to end up with 0.983 moles. It's important to know what it's moles of. Don't forget, this is moles of carbon dioxide. It's very important if we're doing stoichiometry to know what we're dealing with. I've got 0.983 moles of carbon dioxide, and I want to know the energy that's released. So let's go back to our equation. For every mole of reaction, I have 4 moles of carbon dioxide. So I'm going to put my 0.983 moles of CO2 on top. And then, of course, 4 moles will go on the bottom. Then I'm looking for the energy that's released, so X kilojoules divided by negative 3,120 kilojoules. I'm just going back to this once again. Solve for X, just rearrange. 4X equals 0.983 times negative 3,120. Divide by 4. If you want to do that in 2 steps, you're going to end up with negative 767 kilojoules. To wrap this problem up, and then we'll pause the video and move on to the next example. In a process, 750 kilojoules of heat is released. We want to calculate the mass of ethane that is combusted. It's a little different because our given is heat, it's energy. Okay? So if we go back up to our equation, I'm looking for the mass of ethane this time. So I could say I'm really looking for X moles in this case. And of course we still have 2 moles on the bottom. And I've been given 750 kilojoules over negative 3,120 kilojoules. So we just solve it the same way we normally would. We have X moles of C2H6 over 2 moles C2H6 equals 750 over 3,120. Now I need to make sure I'm paying attention to my signs. This is negative 3,120 kilojoules, but this says released, which we learned last class means it's a negative change. That's negative 750 kilojoules. Cross multiply, solve for X. X equals 0.481 moles. Of C2H6, but I was looking for the mass. So I need to do 0.481 moles of C2H6, and we're going to need to multiply by the molar mass. If you needed to do some quick math, you could estimate this. You know that carbon's about 12, hydrogen's about 6. 12 times 2 is 24. You add 24 to 6, you end up with 30. So it's going to be very close to 30. Of course, using the math on using the numbers on the periodic table, you're going to get a more accurate number, which would be 30.068 grams per mole. And you end up with 14.5 grams of C2H6. So we just converted from moles to grams. That's the end of that problem.